What exactly does it mean to say that oxygen has a larger electronegativity than hydrogen, and how do these values affect the behavior of the compounds they form? Firstly, electronegativity is the number we assign to an element based on where it resides on the periodic table. Fluorine has the highest, francium has the lowest, and the noble gases don't have an electronegativity. Conceptually speaking, it describes the behavior of an element when it's chemically reacting. Specifically, it's an atom's tendency to attract electrons to itself within a chemical bond. In chemistry, we represent chemical bonds with sticks in between atoms directly bonded to each other, whereas these dots right here are lone pair electrons. Each bond is composed of 2 electrons, via each donating a single electron for that bond. This electron came from the hydrogen, and this one came from oxygen. And now they're shared amongst both the O and the H. However, these electrons are not equally shared across that bond, because oxygen is better at attracting those electrons to itself compared to hydrogen. That's why we see this skewing of electron density towards oxygen, the more electronegative atom. Since we use sticks to illustrate our bonded pair electrons, we can model the electron density cloud within the model, and it's clear that it's concentrated more towards the center. Likewise, electrons come with a negative charge, so uneven distribution of electrons means uneven distribution of charge. Thus, we have partial charge symbols for different regions of the molecule. So the hydrogen regions are more positive because there's less electron density, and the oxygen region, it's more negative because that's where the electrons are more or less residing. Importantly, charge polarity within the molecule is different from the overall charge of the molecule. The sum of the individual charges must add up to the overall molecular charge. In this case, the overall charge of H2O2 is 0. So that means that the individual partial charges amongst the molecule have to add up to 0, and they do. Similarly, if we had OH minus, the overall charge is -1, so the partial charges would need to balance out accordingly. Another way we can depict electron density disparity is with a dipole moment, which is a crossed arrow pointing in the direction of the more electronegative atom, in this case oxygen, because that's where the electrons and consequently negative charge are skewing towards. Here are 3 ways to depict the exact same thing: one with partial charges, one with an electron density cloud, and one with a dipole moment. The use of partial charges is probably the most commonly used of these 3 because we're likely to discuss how the atoms differ in charge, both within and between molecules, as it has consequences for chemical behavior. The electron density cloud distribution is simply meant to illustrate where the electrons are residing in the molecule or lack thereof. Finally, we use a dipole moment to illustrate the polarity of bonds, such as in identifying the degree of polarity and which one is the more electronegative atom. Notice how the dipole moment not only points towards the more electronegative atom, but the size is also different based upon which 2 atoms make up the bond. So with this information, let's rank the electronegativities of each of these atoms. Right off the bat, we know that hydrogen has the lowest electronegativity because the dipole points away from hydrogen when paired with any one of these other elements. Now we use the relative magnitudes of each of these dipole arrows to see that fluorine must have the greatest electronegativity because its dipole with hydrogen is the largest, and carbon's electronegativity is only slightly larger than hydrogen, and oxygen is somewhere in the middle because the size of the dipole is also somewhere in the middle. We can relate the type of bond any 2 pairs of atoms form based upon the magnitude of the difference of their electronegativities. Now, while I recommend that you are familiar with these ranges and these cutoff values, it's more accurate and I would argue intuitive to view bond polarity on a spectrum with perfect covalent character with no electronegativity difference and perfect ionic character with maximum electronegativity difference. With that, we can say, for instance, that a CO bond has more ionic character than a CH, but it also has more covalent character than a CF. However, while we may compare the polarity of these bonds along a relative spectrum, there are categorical differences between a covalent bond and an ionic bond. In a covalent bond, we share the electrons, but in an ionic bond, the difference in electronegativity is so great that the more electronegative atom simply just takes away the electron or electrons. Nonetheless, there's a bit of gray area as, for example, HF has an electronegativity difference greater than the 1.7 cutoff, so it seems like it would be an ionic bond, but in practice, it's a covalent bond. And that's really to show you that electronegativity difference is just one of the many criteria that goes on into categorizing bicovalent or ionic bond. And it's only when we get in that gray area that those factors are more so considered. Think you understand electronegativity and bond polarity? Well, I have a video on the screen and in the description to help test that knowledge and make sure that you're prepared for your exam.